Hello, I am the muddled Mr. Daycock, and today I'm going to be giving you some examples of using an integrating factor to solve differential equations. So here we are. Let's find the general solution of the differential equation dy by dx minus tan x y equals 1. This is exactly the form we need, because the form we need is dy by dx plus p of x y to be equal to sum q of x. And we have that p of x is equal to negative tan x, and our q of x is equal to 1. This bit is actually not particularly relevant at all. We can kind of just ignore that, but it's part of the definition. Now, that tells us that f of x, our integrating factor, is going to be equal to the integral e to the power of the integral of negative tan x dx. Okay, so now we just need to integrate negative tan. There's a couple of ways of doing this. The way I'm going to show you is going back to our first principles of what's going on with tan in terms of sine and cosine. But alternatively, you can look at the formula, you can look up the rule of what the integral of negative tan x is. But let's have a look at it. So I'm going to say I want to do the integral of negative tan x dx. Well, that is the integral of negative sine x over cosine x dx. Well, the derivative of cosine is negative sine. So in fact, this is the integral of the derivative of cosine of x over cosine of x, because the negative sign is the derivative of cosine of x, and that just integrates to the natural log of cosine of x. Okay, so now we can put a log that in, and we get f of x is going to be equal to e to the power of, and the integral worked out to be the natural log of the cosine of x, which tells me that my f of x is just simply cosine x. And that's my integrating factor. So I can plug in my integrating factor, multiply everything by my integrating factor, and I'm going to get dy by dx minus tan x y equal to 1, and I'm multiplying both sides by cosine x. And that will give me cosine x dy by dx minus tan multiplied by cosine is sine y is equal to cosine of x. And now I need to integrate both sides, and we'll see what we get. Well, the right hand side is easy. Cosine integrates to sine plus c. The left hand side, though, the whole point of the integrating factor was that this is a product rule. It's the product of cosine of x times y, because if I differentiate here, we've had the y differentiated, but here we had the f of x differentiated. So in fact, this whole side, and this is the point of using an integrating factor, is just simply cosine x y. And now for our general solution, that tells us that y is equal to tan x, because I'm dividing by cosine, plus c lots of sec x. And we're done. There we go. This is our general solution. And notice again, as often with these differential equations, the plus c doesn't end up as a plus c. In this case, it's ended up as a multiple of the sec x. Okay, so our next one, let's have a look at our next one. Find the general solution of the differential equation dy by dx is equal to x minus y. Now this isn't in the form we want. The form we want is dy by dx plus p, there we go, it did change, p of x y is equal to q of x. In fact, looking at this, you might think, well, actually, that looks separable. It's not separable because we've got a negative, a subtraction, rather than a multiply. But it's actually quite easy to get it in this form. All I need to do is add the y on. So I'm going to write it as dy by dx plus y equals x. And now this is exactly the right form, with p of x being equal to 1, and q of x, of course, being equal to x. So p of x is 1. So my integrating factor, f of x, is going to be equal to e to the integral of 1 dx, which was very nicely just e to the x. Didn't take a lot to work out our integral. We get our integrating factor of e to the x, and so to solve this, we are solving e to the x dy by dx plus e to the x y is equal to x e to the x. And now we have to integrate both sides just as before. And we'll see what we get. But again, the left-hand side, the whole point of the left-hand side is that it is just going to be e to the x y. That was the whole idea of using an integrating factor, because it's actually just the left-hand side becomes the derivative of a product. But the right-hand side is actually a little bit more of a pain now. We're going to have to use integration by parts with u dash v. Remember our integration by parts formula. The integral of u v dash dx is equal to uv minus the integral of u dash v dx. So I'm going to pick, and my u is going to be equal to my x. So therefore my u dash is 1, and my v dash is going to be equal to e to the x, and therefore my v is e to the x as well. And now we can just plug that into the formula. Our integral of x e to the x dx is going to be equal to uv is x e to the x minus the integral of u dash is 1 times by e to the x, which is our v. And then the integral of e to the x is just e to the x, so this is x e to the x minus e to the x. And so our right-hand side here becomes x e to the x minus e to the x. And then bring it down to simplify it. We get e to the x y is equal to x e to the x minus e to the x. And of course, whenever we integrate here, we need that plus c. So we put that plus c on. And to get our y, we just divide by e to the x, and so y is equal to x e to the x divided by e to the x, we get x. E to the x divided by e to the x, we get 1. And c divided by e to the x, we're going to get minus e to the x plus c lots of e to the minus x. And we're done. There you go. 2 examples of using the integrating factor to solve differential equations. Thank you very much, and I'll see you in the next video.